The first report looked like a misprint. Late August, in the year 1944, just after dawn on the French coast, German technical officers stared at a single line on a crumpled morning sheet from Flak Regiment 155W. 82% of V-1 flying bombs launched toward England the previous day had been destroyed by the coastal gun belt. Not by fighters chasing them, down in dangerous curves. Not by barrage balloons or mechanical failures. By guns. By shells. By mathematics that should not have been possible. These were not superstitious men. They were trained. In the hard, dry arithmetic of ballistic probability taught in Luftwaffe technical schools across the Reich. They knew the tables. For a small, fast target like the V-1, the chance of a direct hit from conventional anti-aircraft fire was supposed to be less than 1 in 10,000 rounds. They had taught those numbers. They had staked doctrine on those numbers. Now the numbers were staring back at them, and the numbers said they were wrong. At the Chateau headquarters of Oberst Max Wachtel, commander of the entire V-1 offensive, the reports piled up across his desk like a quiet accusation. Earlier in the summer, British coastal guns had claimed a modest share of the missiles. 17% destroyed in June. Manageable. Explainable. By late August, on one extraordinary day, the interception rate reached 82%. It was as if the British had bent probability itself. What they were really seeing was not magic, and not a single miracle device. They were watching an entire system click into focus. Radar that could lock and track, guns that could respond automatically, gunners drilled until reaction was reflex, and at the heart of the system. A fuse that moved the explosion from whenever the clock says so to the exact moment a shell entered its optimal lethal bubble around a target. Weeks earlier, no one on the German side imagined such a thing existed. The V-1 story had begun with confidence, almost with arrogance. On June 13th, in the year 1944, exactly 1 week after the landings in Normandy, the first of Hitler's long-promised Vergeltungswaffen, the vengeance weapons, fell on London. At 4:25 in the morning, it came down on Grove Road in Bow, destroying a railway bridge and houses, killing 6 people, injuring 30, and making 200 homeless. The weapon behind that blast represented years of German research at Piemont, a pilotless aircraft powered by an Argus pulse jet, carrying 850 kilograms of amytal at roughly 640 kilometers per hour. It was, in practical terms, the world's first operational cruise missile. Each unit cost about 5,000 Reichsmarks, far less than a manned bomber, and there was no risk to aircrew. Major Walter Dornberger, head of the V-weapon program, had done his own arithmetic. Even if only a quarter of the missiles reached London, the total explosive power delivered would exceed the entire Blitz of 1940 to 1941. Dr. Robert Lusser, responsible for the control system, calculated that interception was nearly impossible. The flying bomb's speed and altitude range, between roughly 600 and 2,700 meters, forced fighters to fly faster than 650 kilometers an hour just to catch it. To destroy it, they had to come dangerously close to a warhead that would tear them apart if it detonated. As for anti-aircraft guns, the science seemed merciless. Small, fast target, limited engagement time, manual time fuses that had to be cut and set by hand. Lusser's estimate, less than 1 hit in 10,000 shells, was not some propaganda flourish. It was the honest conclusion of the mathematics Germany trusted. Faith, in this case, was placed in calculus and slide rules. For a little while, reality cooperated. When the first waves of V-1s crossed the Channel, Britain scrambled to adapt. Gun positions were reorganized, predictors recalibrated, crews retrained under pressure. By late June, Germans listening to British claims of 10, then 24% interception could shrug. That was higher than expected, but still within the bounds of imagination. Gunners could improve with practice. Fighter pilots could develop tactics. Then July came. The percentages climbed, and the ammunition expenditure per kill, as estimated by German observers, began to fall into a range that no existing theory could support. From the French coast, officers watched V-1s humming steadily toward England, only to see clusters of bursts form around them at just the right distance, not touching the missile, not striking it cleanly, but near enough. The bomb would suddenly tumble, break apart, vanish into smoke. Again and again. Too many times to wave. Away as luck. German intelligence had, on paper, been warned. An early pre-war document, the so-called Oslo Report of November in the year 1939, had mentioned Allied experiments on proximity fuses. German scientists had dismissed it as clever disinformation. Their own attempts at similar devices had gone nowhere. More than 30 concepts had been explored, none had survived. The gauntlet of technical demands. To make a proximity fuse work, someone had to shrink radio transmitters and receivers down to a device that could fit in an artillery shell. The vacuum tubes had to endure 20,000 times the force of gravity when the gun fired, and the shell leapt from the muzzle spinning at 25,000 revolutions per minute. The batteries had to sit for years on depot shelves and then come alive on command every time. Every one of those problems seemed just beyond the practical reach of German industry under wartime stress. The conclusion was simple and comforting. It could not be done. So when, in January of the year 1943, the cruiser USS Helena in the Pacific shot down a Japanese dive bomber with a shell that detonated itself when it sensed the target, no one in Berlin understood what that meant. The success stayed in Allied circles, recorded in quiet technical reports and restricted files. The device that made it possible was given a deliberately misleading name, variable time, or VT, as though it were just another clever clockwork. By the summer V-1 campaign against Britain, American factories were already producing 40,000 of these fuses every day. But a fuse in a crate is only a promise. To turn that promise into the 82% that haunted Wachtel's desk, a whole chain had to be forged. On the British side of the channel, that chain was built step by step. Anti-aircraft guns were pulled back from the North Downs and redeployed to the South Coast. Concentration, not dispersion, became the guiding idea. A gun that missed over inland fields might send a secret shell into German hands. A gun that missed over the water lost only steel to the sea. The coastline became a belt, a single great battery whose job was not to protect the city by its limits, but to reach out and meet the threat as it crossed the line of surf. Behind those guns sat American SCR-584 radar sets, the product of another industrial miracle. They could search, acquire, and then automatically track a small, fast target across the sky, feeding data to analog computers that spat out firing solutions. Human eyes still watched. Human hands still worked the elevation wheels and loading trays. But the core of the problem, the speed, the prediction, the place where mistakes usually crept in, was handed off to electronics. The shells themselves carried the last piece. Inside each VT fuse, tiny vacuum tubes made by companies like Sylvania Electric and Western Electric pulsed radio waves into the air ahead of the projectile. As long as the signal bounced back from empty sky, the circuit remained quiet. When those reflections changed in strength and timing, when a solid object, a V-1's metal skin, entered a defined proximity, a thyrotron switch triggered the detonator. The shell waited not for a pre-cut time, but for geometry. The effect, in the kill zone over the channel, was simple to describe and very hard to survive. Before VT, it took an average of 2,500 heavy shells to bring down a single V-1. Most bursts blossomed a little too early or a little too late, throwing fragments into harmless air. With VT fuses timed by distance instead of by best guess, that number dropped to about 100. The proportion of flying bombs destroyed by the coastal guns rose from 17% in June to 74% by late August, and on that one remarkable day in the final week, to 82%. From the German coast, it looked like sorcery. From inside the British command system, it looked like work. Crews drilled until the steps blurred together, radar acquisition. Data fed forward, guns laid on bearing and elevation, ammunition issued with special accounting. Officers checking and rechecking procedures for handling the new shells. Anti-aircraft units and RAF. Regiment squadrons shifted positions, learned new fields of fire, synchronized with searchlight crews and observers. Technical manuals were updated and quietly circulated. The VT fuse was a star performer, but it was part of an orchestra. The men firing those guns were not told the details of what sat in the nose of their shells. They only knew that they were handling ammunition under Extraordinary security. Each round was counted out. Each spent casing was tracked. Any dud shell that landed on British soil was guarded until specialists could recover it. Naval vessels patrolled the waters where V-1s were engaged, ready to deny the Germans even a fragment that might give away the secret. That secrecy had a cost. Allied ground forces in Europe were not allowed to use VT fuses against German troops until December of the year 1944 at the Battle of the Bulge. Thousands of soldiers who might have been saved by more effective artillery died in the months when the technology was held back. The choice was brutal but simple. If Germany obtained a working sample of the fuse too early, the entire advantage could evaporate. If London fell under the V-1 bombardment in the first months after D-Day, everything else on the Western Front became fragile. On the other side of the Channel, inside Flak Regiment 155W, all that was invisible. Wachtel and his staff did what professional officers do when confronted with ugly data. They questioned their own system first. They suspected sabotage, manufacturing defects, navigation errors. Emergency inspections were ordered. Missiles were torn down, checked, reassembled, test fired over German territory. Every time, performance fell within expected tolerances. Guidance worked. Engines pulsed steadily. Altitude held. The problem appeared only when the V-1s reached British defenses. German scientists and engineers in Peenemünde were forced toward a conclusion they did not want to accept. If the British were not cheating on their reports and the missiles were not failing on their own, then the defenses had changed in some fundamental way. Improved radar, perhaps. Faster fuse setting mechanisms. Better predictors. They could imagine refinements. They could not imagine a shell that sensed its own target. They tried tactical workarounds. Launches were shifted to different altitudes, in larger salvos, at varying times, in weather that might blur radar echoes. They used night, cloud, and rain as allies. The kill rates stayed stubbornly high over the coastal belt. The V-1 was behaving, as a system, exactly as it had been designed. The system it was flying into had quietly evolved beyond the assumptions on which that design rested. In that discrepancy between what German engineers believed was possible and what American and British engineers had actually built, lay one of the war's most important intelligence failures. The industrial story behind the VT fuse was nearly as incredible as its performance. The device itself cost hundreds of dollars per unit when it first entered production in the year 1942. By the end of the war, careful redesign and scaling had driven that cost down to about $18. Over the course of the conflict, the United States would manufacture some 22 million proximity fuses at a financial cost exceeding $1 billion wartime dollars. The Crosley Corporation, which had made consumer radios and refrigerators before the war, was turned into a fuse factory. At its peak, it employed 10,000 workers and turned out 16,000 fuses a day, more than some entire Luftwaffe units could fire. Sylvania Electric devoted its vacuum tube research and production almost entirely to the rugged little glass and metal cylinders that lived inside those fuses, producing roughly 400,000 miniature tubes daily. Monthly American output of proximity fuses eventually exceeded total German production of V-1 missiles for the entire war. Abundance, not ideology, won the war. Germany, under blockade and bombing, handcrafted weapons in underground tunnels with slave labor. Tens of thousands of concentration camp prisoners died in the production lines for V-1s, crushed by rockfalls, suffocated by fumes, starved and beaten to death to bring a weapon into the world that would, more often than not, detonate harmlessly over the sea. In the United States, women at places like Sylvania's Ipswich plant worked 12-hour shifts soldering and assembling components for a device they were told almost nothing about, except that it mattered. They collected overtime wages, went home to families, and only after the war learned that their work had helped save London. The contrast was more than moral. It was structural. Totalitarian systems could issue orders and demand sacrifice. They struggled to coordinate scientists, engineers, factory managers, and line workers in the open, iterative way that complex electronics required. Dr. Merle Tuve, the physicist who led proximity fuse development at the Johns Hopkins Applied Physics Laboratory, later pointed to this as the real advantage. The fuse was not just a triumph of clever circuitry. It was a triumph of cooperation. By September of the year 1944, the numbers spoke for themselves. Of the 9,521 V-1s launched from ground sites against Britain, only 2,515 reached London. 6,184 civilians were killed and 17,981 injured. A tragedy on any human scale, but a fraction of what had been intended. General Frederick Pyle, commanding Britain's anti-aircraft command, estimated that without proximity, Fuze's casualties would have been 4 to 5 times higher. The V-1 offensive that Hitler had once imagined would break British morale became, instead, a statistical demonstration of how fragile a wonder weapon can be when it meets a better organized system. Even when the Germans briefly held American ammunition dumps during the Battle of the Bulge and physically captured VT fuse shells, their own assumptions betrayed them. The fuses were examined and misfiled as improved. Conventional designs. The idea that a radio transmitter and receiver could survive gunfire in a shell nose was simply too far outside their mental frame to be recognized. They had, literally, held the secret in their hands and let it pass. They did not just lose a battle, they lost their idea of the world. After Germany's surrender, Allied interrogators sat down with officers like Wachtel and with technical experts who had spent the war trying to explain the collapse of the V-1 offensive. Shown the internals of American VT fuses, German scientists reacted first with disbelief, then with a kind of exhausted respect. Based on their own research, they judged themselves to be roughly a decade behind what the Allies had achieved in ruggedizing electronics for artillery use. By then it no longer mattered. When the veil of secrecy was finally lifted in September of the year 1945, the U.S. War Department announced the proximity fuse as one of the most important weapons developed during the war, surpassed in effect only by the atomic bomb. That comparison was less about raw destructive power than about leverage. The atomic bomb created entirely new kinds of destruction. The proximity fuse quietly multiplied the effectiveness of every gun that used it by a factor of 5 to 10. Faith cannot armor steel. The V-1 had embodied the German belief that a single advanced weapon, engineered to the edge of possibility, could compensate for dwindling resources and strategic setbacks. The proximity fuse embodied a different philosophy, that the real power in war lies in making existing tools work dramatically better and then producing those tools by the millions. Germany built brilliant individual weapons. America built good enough weapons in overwhelming numbers and paired them with systems that made every round count. The V-2 rocket that followed the V-1 could not be intercepted at all with the technology of the time. It slammed into London and Antwerp without warning, beyond the reach of radar-directed guns or proximity fuses. But it arrived too late, in numbers too small. At a moment when Germany's larger position was already collapsing, raw technical sophistication could not claw back what had been lost on the assembly lines. In the years after the war, the circuitry and principles that had made VT fuses possible evolved into peacetime technologies: radar altimeters for aircraft, more reliable radio components, the early foundations of modern air defense systems, and electronic warfare. For the German scientists who had once stared at baffling kill rate reports from the Channel, the proximity fuse remained a painful reminder. It was the ghost of a blind spot. On that late August morning in 1944, though, all of that lay in the future. What existed in that moment was simpler: a report on a desk, figures that did not add up, and far out over the gray channel, a line of V-1s droning toward England. One by one, they flew into a patch of air where mathematics had quietly changed sides. Radar beams reached out. Analog computers spun their gears. Gunners worked in routine motions that came from long, exhausting training. And tiny radios, buried in steel and circuitry at the tips of shells, listened to the echo of their own signals until a certain pattern emerged, the pattern that said, "Now." A flash, a cloud of fragments, a broken arc of flaming fuel and falling wreckage. That never reached London. The Germans watching from afar saw only the explosion and the failure. They never saw the invisible structure behind it, the radars on their concrete pads, The women in Ohio and Massachusetts soldering tubes, the physicists in Maryland arguing over test data, the British crews in muddy gun pits counting shells. They launched roughly 25,000 V-1s in all theaters over the course of the war. They never truly understood why so many of them died in midair. The proximity fuse turned Hitler's vengeance weapon into London's shield. It did so through thousands upon thousands of small, precise bursts, each one the end of a long chain of design, production, training, and secrecy. In the end, the decisive battlefield was not over the city or even over the channel. It was inside factories, laboratories, and test ranges where an open society harnessed its science and industry to solve a problem it believed could be solved. The 82% interception rate recorded on that single day in late August stood not just as a statistic, but as a quiet verdict on modern war, that in a struggle of systems, the side that can imagine, build, and mass-produce effective answers will break the weapons of the side that cannot. Even when those weapons look, for a time, unstoppable. They had done everything, right by their own understanding. They had built a fast, fearsome missile, trained elite crews, and poured scarce resources into a program they believed would turn the tide. But as their V-1s fell, burning from the sky, they were being defeated by millions of tiny devices they could not see, in a technological language they had decided in advance was impossible. And by the time they finally learned how those shells had really worked, the war those weapons might have influenced was already over.